Welcome to the fourth lecture of this year's internet seminar. So for the moment you see that we're keeping the rhythm. Robert did lecture 3, previously did lecture 1, so for the time being it's me doing the even integers. I picked up the same shirt as in the last lecture so that you don't take me for someone else. I'm still Moritz, and today I'm going to talk about Fourier analysis and the Laplacian. And I'm also going to talk about that in the second lecture. So in the grand scheme of things, what are we trying to do? So last lecture, you've seen that we can introduce some spaces that combine Hilbert space structure and differentiability properties of functions. So differentiability was then in a new sense, we called it weak derivatives, and these so-called Sobolev spaces allowed us to apply the form method that you learned about in the second lecture in order to define differential operators. So what we did is we defined elliptic differential operators in divergence form with L-infinity coefficients as a special case of the form method, and the most beautiful of all operators in that setting is of course the Laplacian, corresponding just to coefficients being constantly identity metrics. And that worked on every open subset of Rn. Now, just the abstract form methods is not going to be enough for the things that we want to do in this internet seminar. And so the whole seminar will somehow take place in between abstract methods like form method using Hilbert space structure, and then methods from harmonic analysis that really use that you're working on Rn, and you can do manipulations with integrals, and you can do further things, introduce further structure to the problem, allowing you to prove more interesting things. And so as a primer of many of the things that we want to do in lectures 5, 6, 7, 8, we're gonna look just at one operator, namely the Laplacian, and I'm gonna work on R to the n, so on the full space, there's no boundary conditions, and I'm gonna use the Fourier transform to provide alternate descriptions of the objects that you've seen so far. Okay, so that's the plan. And then these Fourier analysis as a very particular tool offering a very rich structure to all of the objects that we're interested in will give us some guidelines of what we should try to do if we want to prove similar results for general operators. Okay, so that's somehow the plan. So in particular, after these 2 lectures, you will see that there are things like fractional powers of the Laplace operator, or to be precise, the negative Laplacian, because the negative Laplacian is the operator that corresponds to elliptic, accretive, and bounded sesquilinear forms. So you will see that this is a fractional power, and for the moment it's completely unclear what should it mean to apply just a quarter power of the operator. I mean, for sure you know how to apply Laplacian, how to apply it twice, 3 times, 4 times, and so on, but what a quarter? It's not so clear. And then we're going to look to Sobolev spaces on Rn. And so you know that there's H1, there's H2, H3, and so on. There's also H0, which should be L2. But what's not so clear, and which somehow is related to studying these fractional powers of operators, are Sobolev spaces of fractional order. Okay? And so there's going to be, for example, a space H1 half, and I'm going to make very clear, hopefully, what half a derivative intuitively should mean. And also we see that these 2 objects, they are somehow related. Okay? So there is going to be a relation, but that has to wait until maybe end of this lecture or the second lecture. Okay, so what we need to do all these studies is the Fourier transform. And so before really getting our hands dirty and working with it, we're going to recall some basics of the Fourier transform. Okay, so we do hope that you all know this, but just in case that you forgot something or you're uncertain about certain notational conventions, we're going to give a list of the basic properties that we're going to use in this lecture, and then we're going to use them freely without referring to them every time we're going to use them. Okay, so first of all, what is the Fourier transform for us in this lecture? So here's a definition. If U is L1 on Rn, then Fourier transform of U, written with a script f, or sometimes also just U hat. This is an integral transform of U, where you integrate over all of Rn, and then our convention is going to be that we put e to the minus 2 pi I x times xi u of x dx, and this is defined for all xi in Rn. So it turns a function on Rn into another function on Rn, and then there's the inverse Fourier transform written as a script inverse of U, typically then evaluated at x, because x is somehow the space variable and then xi is the frequency variable that you're going to achieve when you apply Fourier transform to a function living in x, and then inverse Fourier transform takes it back, so that's like the check, and then check is basically the same transform except that you change the minus into a plus sign. Okay, and that's for all x and r to the n. Okay, so this is our Fourier transform. This is our inverse Fourier transform. When you work with a Fourier transform, you should recall that there's one particularly nice space that is helpful because it's a space of smooth functions that are integrable to all powers and that is left invariant under the Fourier transform. Okay, this is the so-called Schwarz space, so we say that U is in the Schwarz space on Rn. This means by definition that all derivatives of U exist and they are decaying faster than any polynomial. Okay, in other words, whenever I pick multi-indices alpha, beta, n naught to the n, I can say that the sup in x over x to the alpha d beta of U, this sup is finite. Okay? In other words, every derivative of U, like d beta of U, decays at least as fast as any monomial, and therefore all polynomials, x to the alpha. We use the usual multi-index notation, saying that x to the alpha, this is the same as x1 to the alpha 1 dot 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 xn to the alpha n. Okay? I hope you're cool with that. And so Schwarz space is the basic space from which you start building your Fourier transform. Okay, and then Fourier transform is going to be useful because of all the transformation properties that we're going to have for it. So maybe I'm brave enough to use this board over there and then keep the properties for the whole lecture in the hope that I don't have to clean in between. And so in this proposition 4.2, it's just a recap of all the properties that you hopefully already know. Okay? In case you haven't seen some of them in the ISAM lecture notes, we give a reference to textbook. You can look all these things up. Okay, so what's the proposition? So suppose that U and V, they're Schwarz functions, then maybe I want to take a vector in Rn, I want to take a multi-index because I want to look at derivatives, and I also take a positive number because I want to study, study is a fancy word for someone just writing something down without proving anything, but I want to recall what's happening when I do dilations and then Fourier transform, okay? So property A is what I already told you. If I apply Fourier transform to a Schwarz function, then I get back into Schwarz space, and the same goes for the inverse Fourier transform. And the names are not by coincidence, because these two transforms are really inverses of each other. Okay? And so let's write it down maybe. Okay? Inverses of each other. All right, then the most important property for all of the things that we're going to do, because we want to study differential operators, is what does Fourier transform do with derivatives of functions? Okay, and the beautiful thing, as you all know, is that if I differentiate a Schwarz function, this is still a Schwarz function, I can take Fourier transform, and then the Fourier transform turns the derivation into a multiplication by a nice function, which in this case is 2 pi I xi to the alpha times u hat. Okay, so on the level of Fourier transform, derivatives is just multiplication by some nice monomial. Okay, then number C, I want to do two things. I want to look at dilations and translations. Okay, so delta t of u dot is u of t dot is the dilation, and tau y of u dot, this is a translation, so it's dot minus y, and this is called translation. Okay, and so what's happening when I apply Fourier transform? You recall it? So if I do dilation and then Fourier transform, then what I get back is t to the minus n times a new dilation, but going from t goes to t to the minus 1, okay? And then you dilate the Fourier transform. In other words, if you think of the mollifier writing, this guy is just the mollifier associated with the Fourier transform of u. Okay, so this is u hat t. Mollifier writing of lecture 3, and this is how I usually recall it. Okay, so dilation, you multiply the argument by t, then you apply Fourier transform, then it goes into the mollifier family attached to the Fourier transform of u. And the second rule is that a translation under the Fourier transform turns into modulation. So this means it gives e to the minus 2 pi I y dot u hat. Okay, so it's a modulation on the Fourier side. Okay, these are more like algebraic properties. Then there's the beautiful rule that tells you that if I do convolution of two functions and the Fourier transform, this gives the product of the two Fourier transforms. And finally, there's Parseval's formula telling you that if I take the L2 inner product of these two Schwarz functions, it's the same as the L2 inner product of the respective Fourier transforms. Okay, this is usually called Parseval's formula. In particular, when you set u equal to v, and you see that u and its Fourier transform have the same L2 norm, which is called Blancharel's identity. Okay, so this is property f. U L2 squared is the same as u hat in L2, and is also the same as the inverse Fourier transform, and this is called Plancherel's identity. Okay, fantastic. So this is the things that we're going to use. Okay, I guess you've seen them all before. One kind of stupid remark, but it's helpful, is that you have similar rules for the inverse Fourier transform. Okay, similar rules for U hat. And why is this? This is simply because when you go back to the definitions over there, inverse Fourier transform at a point is just the same as Fourier transform at minus this point. Okay, so if you want to write down the respective rules for the inverse Fourier transform, you obey this rule and then you write down what you get. The most important thing for this lecture is the consequence of these E and F things using the fact that the Schwarz space S is dense in L2. Okay, why is this? I mean, first of all, because the functions are rapidly decaying, you can check that they're in L2. And then density just follows from the fact that already CC infinity is dense in L2, and so in particular S is dense in L2. Okay, so S is a dense subspace of L2, and then this thing tells you that Fourier transform is a linear isometry with respect to L2 norm, and it maps S into S, it maps S onto S, so it extends to an isometric isomorphism on L2, and this is what we mean when we talk about the Fourier transform on L2. Okay? So I'm not going to use a different symbol if I want to talk about Fourier transform on L2. I'm just writing a script F as before. The only thing I have to remember is that, of course, I'm not allowed to use the representation formula anymore. Okay? So let's write it down and say that by density, Fourier transform from L2 into itself is an isometric isomorphism. And we're going to use the same symbol for this L2 Fourier transform, and this fact is sometimes called Plancherel's theorem. Okay, so as a little exercise for you guys and also for everyone watching the video, I'll leave the following thing. You make the observation, someone of the four virtual lectures tries to be very precise using Parseval's formula, Plancherel's identity, and Plancherel's theorem. Honestly, I don't care at all. I just call them all Plancherel. Okay, but you can make a guess who is insisting on that. I don't know. Maybe on the workshop we're going to tell you who it was. For me, it's a pain in the ass. I'm going to call all of them Plancherel, if you don't mind. Okay. That's a good thing when you do the lecture. You have one final shoot on all the things that you try to change in the writing process, but then somehow majority vote was against it. Anyway, that's a different story. What I want to tell you is that the fact that now the Fourier transform extends to L2 by density naturally raises the question, which of these properties in the list also extend to L2? Instead of just the Fourier transform on the Schwarz function. So I'm going to use some color chalk to talk you through. So of course in A there's nothing to do. B I'm going to talk about at the very end. The transformation rules in C by density, they're going to extend to L2. Okay, so let me just write down that's okay for U in L2 Rn. Straightforward density argument. Then the convolution thing, I say this is okay when, say, U is in L1 and V is in L2, or the other way around. and we're going to refer to the exercises for this to make this extension by density. It's not deep if you've seen it before. It's also good to keep in mind what you have to do in order to make that thing work. Then these two things, they are okay, of course, for u v in L2, because this was how the L2 Fourier transform was being constructed. Okay. And now the interesting thing is, what about this second rule that I somehow advertised as the most interesting one, because it talks about derivatives, making derivatives structurally easier by turning them into multiplications. Okay, so here's really a question. I mean, what about more general functions? And you see that by just asking you what I should do, naturally I go in the direction of Sobolev spaces, because now I have an L2 Fourier transform. So the natural framework for this would be L2 function, which is the same as u hat being L2, for which also this left-hand side would make sense in virtue of the L2 Fourier transform. So naturally I'm going to talk about functions such that d alpha of u is in L2. So I'm in the realm of Sobolev spaces. The Sobolev spaces are the natural framework to extend this rule B when I want to use the L2 Fourier transform. Okay, and so I'll leave these properties over here, and then substantial part of this lecture is going to be to explain how indeed Sobolev spaces and the Fourier transform on L2 work together, and indeed in the end we will be able to extend this property B in the right way. Okay, so you stop me if you have questions, as usual, right? So 4.2, now I have to look up how we call this section, the domain of the Laplacian on Rn. Okay. So you see, in the end, we want to describe the variational Laplace operator from the last section using the Fourier transform, but in order to get there, we have to talk about Sobolev spaces and the Fourier transform. Okay, so the first goal here will be to understand Sobolev spaces via the Fourier transform. So this is like a two-sided understanding, because I want to understand what Fourier transform does with the Sobolev spaces, but at the same time this will offer a new perspective on Sobolev spaces, which is very natural in view of these transformation rules. Okay, and so here's the result that achieves this goal. If I fix k a natural number, which is going to be the order of the Sobolev space, then here's an alternative description of the Sobolev space in terms of Fourier transform. So hk of Rn are precisely those L2 functions for which the function mapping xi to norm of xi to the k times Fourier transform of u, this function is in L2. So Sobolev space means L2, and the Fourier transform is square integrable if you multiply it with this weight factor related to the order of the Sobolev space. Okay, and in addition, this is somehow not, it's not just an equivalence of sets, but it's an equivalence of spaces. Please, there's a question. Yeah, there should not be a colon. That's not a definition. That's That's a fact. Okay. I could also make a definition, but then I would have to prove the reverse theorem to it. Okay. This thing is not just equality of sets, but it is equality of spaces. So, in other words, the HK norm of a function is comparable to the natural norm that is associated with this set, which would be u in L2, and this function measured in L2. Okay. Okay, and moreover, and this has to be proved on the way, this formula 4.2b is going to be valid for the weak derivatives of an hk function. In other words, moreover, 4.2b is valid for u in hk and multi-indices, of course, of order less than k, because otherwise they are meaningless to the hk space. Okay, so you can compute the Fourier transform of the weak derivatives according to the rule that you're used to. Okay, let's try to prove this. So here's the key observation. So at some point I have to use Fourier transform and I have to use weak derivatives. So in the most general setting, I would probably be interested in a L2 function and a Schwarz function. And then I need to look at the expressions like the integral of u times d alpha v bar, because I want to use L2 inner products. Okay, and I put a minus 1 to the absolute value of alpha, a factor that you're very well aware of, that always shows up in the definition of the alpha order weak derivative. Okay, and for example, if I would know that the function u would be in a Sobolev space and alpha would be less than the order of the Sobolev space, then I can use the definition of weak derivatives and I can move the derivative around so I can work with this expression. This is going to be helpful for one direction, but before even doing that, I want to stick to the general expression where I'm not allowed yet to do this integration by parts, and I just want to use the Fourier transform to do stuff with it. Okay, and what I can always do here is I can use Plancherel, and I can stick with this factor, and then instead of having L2 inner product of the two functions, I can have L2 inner product of their Fourier transforms. Okay, and then I can use 4.2b, because this is a Schwarz function. I know what the Fourier transform does. So it's going to give me a multiplication with this 2 pi I xi to the alpha. So let's put it here. Then u hat, and then it's going to be v hat bar d xi. Okay, and it's correct like this because the 2 pi I xi would pop up in the antilinear component of the product. And so if I move the pi out to the first line, I'm going to get a minus 1 to the absolute value of alpha, which is cancelled by this one. Okay, so it's correct with this, and the minus 1 normalization thing has disappeared. Okay, so that's just a fact. Let's call this fact 4.1. I mean, if you want to, if you would do the proof yourself, this is probably a thing that you would write down at the early stage of the proof, because at least that's a calculation that uses all the things that you have to use at some point without doing much. Okay, but it's going to be helpful. But now we have to invest further information in order to prove this proposition. Okay, so I'm going to start with the inclusion of the Sobolev space into the right-hand side. Okay, so suppose U would be in HK, not just in L2, and suppose that alpha is of order less than K. Okay, now what I'm going to do is I'm going to start out on the right-hand side of this 4.1, so I'm just copying this expression. 2 pi I xi to the alpha u hat times v hat bar dxi. Okay. Then I'm reading this line backwards. I get here. But now the fact that u is in hk allows me to do something more with this part. Okay. So I can rewrite the orange part using the definition of weak derivatives. So here, strictly speaking, I'm using the fact, because this v is not a CC infinity function, but you've seen in one of Robert's lectures that by this density argument, the integration by parts formula on hk can be symmetrized. So you can use test functions in hk for u in hk, and in particular I can use Schwarz functions. Okay, and so definition of the weak derivatives allow me to move this thing in the weak sense, and so the orange part just becomes the integral on Rn, and then it's d alpha of u times v bar dx. Agreed? Okay, but now I can use Plancherel again, and I get that this is just the same as d alpha u hat times v bar hat dxi. Okay, amazing. So I want to prove something about the weak derivatives of u, and you see this looks a lot like saying that the Fourier transform of this weak derivative should be the same as this function, which would be precisely the 4.2b that I want to prove. The only thing, if you want to really reduce this to the fundamental lemma in the calculus of variations, is to worry a little bit about the functions that I'm testing with. Okay? And I claim that this so far is valid for every v in the Schwarz space. I claim that instead of having any v in the Schwarz space, I can put phi here, and I can put phi here, where phi is any CC infinity function. Okay, and how do I do that? Well, any CC infinity function can be written in that way by just taking v to be, well, I first take the inverse transform of phi, and then I take a bar, or the other way around. Okay? If I take this v, then v hat is going to be phi bar, and then v hat bar is going to be phi bar bar is going to be phi. Okay, so the flexibility of having v any Schwarz function allows me at this point to reduce to all CC infinity functions, so I can use the fundamental lemma in the calculus of variations to conclude that this locally integrable function is the same as this locally integrable function. Okay? This guy is locally integrable. I don't know much more about it, but locally integrable is fine. Okay, so this is the fundamental lemma with which number? 3.4. 3.4 says that d alpha u hat is the same as 2 pi I xi to the alpha u hat. Maybe with xi, and maybe be careful and say for almost every psi. Okay, sweet. So we have proved the formula for the weak derivatives. Okay. Let's stick with this information for the time being and see what we can do when we go the other way around. Okay, so I mean, of course, the polynomial here is not the right one compared to here, but we're going to sort things out in the end. Okay, so if I want to go in the other direction, I'm going to suppose that u is in L2, and that additionally this function here is also L2. Okay, so UL2 is the standing assumption, so I just write down that xi going over in xi to the k u hat of xi, that this function here is in L2. Okay, and now I want to go the other way around, and I want to see that I can weakly differentiate the function, and the weak derivatives are going to be in L2. Now I know already from this observation that the weak derivatives should be precisely the functions whose Fourier transform is given by this expression over here. Okay, so my goal is that I want L2 functions that I'm going to call u alpha with a property be the Fourier transform of the alpha's weak derivative of u. So I want these functions with u alpha hat being equal to 2 pi I xi to the alpha times u hat. Okay, maybe with a dot notation. So does that work? Can I define a u alpha function on the Fourier side by this expression? Well, you know that the Fourier transform is an isometry from L2 into L2. So if I want to define u alpha in L2 with this property, I just have to make sure that this function here is L2. Then I take its inverse Fourier transform and I'm going to call it u alpha, and I'm done. Okay, and so I claim that this here is in L2. And why is this the case? Well, you estimate 2 pi I xi to the alpha in absolute value, first by 2 pi to the absolute value of alpha times xi to the absolute value of alpha, and then you can try to play it back to the thing that you know to be in L2 by saying, well, 2 pi to the alpha, this is just a number. Then there are two cases. I claim I can estimate like this. And why is this true? Because this power here is less than k. So if xi in absolute value is smaller than 1, I can just bound this guy by 1. And if xi in absolute value is larger than 1, then I can bound this power, this monomial, by a polynomial of higher degree. And so the estimate is also true. Okay, so I have this estimate. In other words, this factor sitting here is controlled by the sum of these two factors. Well, a factor of 1 hitting u hat gives an L2 function, always, because u was L2, and a factor of xi absolute value to the k hitting this guy gives an L2 function by assumption. So indeed, there is a u alpha in L2 that satisfies this relation. Okay, and so once I have this function, I can just start doing calculations again. Okay, so now what can I do? I can look at 4.1. Okay, and I start with the left-hand side of 4.1, just copying this time. So this is the integral of Rn u times d alpha v bar dx. But now the additional information that I'm having here allows me to do something on the right-hand side. Okay, so let's color the right-hand side in blue. Okay, and on the right-hand side I can do something. Namely, what is sitting here is just the Fourier transform of this newly defined function u alpha. Okay, so this is going to be integral on Rn u alpha hat times v hat bar dxi, and then you do Plancherel again to eliminate all the hats. So it gives you this. Okay. And now this calculation works for every Schwarz function, so it also works for every CC infinity function. If you want, you can put the bar here, and then you see, instead of having v bar in Schwarz, you can again just have phi, a test function. So phi is in CC infinity. And then you see you checked definition of weakly differentiable. So indeed, u is weakly differentiable of order alpha, and the alpha's weak derivative is precisely the function that's sitting here. Okay? So this means d alpha of u is equal to u alpha in the weak sense. Okay, and because this works for all of these multi-indices, it follows that u is in hk. Okay. So far we have proved the formula for the derivative, and we have proved completely the inclusion from the right into the left. What's missing is the inclusion from the left into the right, because we stopped here and we need to prove the norm equivalence. Okay, and these two things I'm going to do all at once. So norm equivalence. This is just some stupid comparison of polynomials. Okay, so for an hk function, what I do know is I know how to compute the hk norm. This is hk norm squared. This would be L2 norm squared, and then the sum over all of these derivatives, all in L2 norm squared. Okay, but I know a Fourier formula for the derivatives, and I know I have Plancherel's theorem, so L2 norm is the same as L2 norm of the Fourier transform. In other words, this is the same as the integral of u hat of xi squared times the sum over all multi-indices up to order k of 2 pi I xi to the alpha squared dxi. Okay, and so this guy here is a polynomial. Gonna call it p of xi. And now what I have to prove is that this p of xi is bounded from above and below by the two things that I'm allowed to use in this theorem, namely a 1 referring to the L2 norm of u, and this xi to the k squared referring to this function, which I'm also putting in L2. Okay, so we need just a two-sided estimate of the polynomial. How can I do that? Well, let's see. If I want to bound, it's always easier to bound things from above. So if I want to bound this polynomial from above, I can basically do a calculation very similar to the one above. Okay, so you get all these monomials. Every of these terms I can bound by absolute value of xi to the 2 absolute value of alpha, so it gives xi to the 2k, so there's going to be a constant depending on the dimension, with the property that this is going to be 1 and 2 to the k as a power for psi. It's the same type of calculation, except that in the intermediate step you have a squared, and so you have the double power. Okay, so this is the estimate from above, and so this estimate tells you that if I control u and this guy in L2, then I control all of the other guys. So this is one direction. And then we need the lower bound. The lower bound, by the same type of term, will also complete the discussion of this inclusion, because here we controlled all of these things in L2. So if the control of all of these things in L2 implies the control of this guy in L2, then I also completed the direction going from hk to this guy. Okay, and so how do you do that? You look at this polynomial, you single out some interesting terms, namely when the multi-index is 0, then you get a 1, and then you just look at the multi-indices that are purely of order k in one direction, so k times the unit vectors, and so this is going to give you sum in j 1 to n, psi j to the 2k. Okay, and then a monomial like this is some sort of equivalence of norms on finite dimensional spaces. You can make it explicit using Hölder's inequality. I'm not going to do it here, but you can bound this by 1 plus psi squared to the k. Okay, if you want. It's just a Hölder's inequality. Or you can see it in the appropriate way as an equivalence of different norms on the finite dimensional vector space Rn. Okay, and so this polynomial is squeezed between these things, so it's comparable to this guy. And so this hk norm is comparable to just these two terms, which gives the norm equivalence, and at the same time it says that if u is in hk, then we have this in L2, and the knowledge of this in L2 implies the knowledge of this in L2, and so the proof is complete at this point. Oof. Do you have questions? No, so let's make 10 minutes of a break for you guys, and no break unless you want it for those guys watching online, and then we're going to see what we're going to do with this theorem. Okay. Okay, so... Ooh, sound is wow. Anyway, okay, so we proved this theorem which shows you that using the Fourier transform, hk is just the space of all L2 functions, such that this additional L2 function is also in L2. Okay, that's what we proved, and now we're going to use that to somehow justify the title of this subsection. Okay, so as you see, I just removed the proof from the board, and I put the next theorem right below it, and this theorem is going to give you a description of the domain of the negative Laplacian on Rn. Okay, so minus delta h1 Rn. Looks a little bit strange in notation, but reminds you that this is the negative Laplacian defined by the form method of the last lectures, and the form domain, if we're working on Rn as the open set, is just h1. Okay, so this is our understanding of the Laplacian using sesquilinear forms. So this is the negative Laplacian on Rn. And what we're going to say in this theorem, okay, so now, as in 3.26, is that the domain of this operator, which, if you recall definition using sesquilinear form, was one of these non-script L operators, the domain of which was defined by saying that the sesquilinear form could be represented with respect to the H, in this case L2 inner product, but this domain that you get is just the same as the Sobolev space H2. Okay, so this is H2 on Rn. Okay, and moreover, this goes with equivalent norms. Okay, so there's the H2 norm here, and then there's the graph norm on the domain, as always, if we don't say anything further. And moreover, this form method Laplacian, acting on a function in its domain, which now is the same as H2, this form method Laplacian does precisely what the Laplacian does. And if you're an H2, then you can take all second-order derivatives in the weak sense. So there is an object minus Laplacian of u defined in the H2 sense, and this is precisely the same as what this variational operator gives you. Okay, so this holds for all u in the domain of the variational operator. Okay, so this here is in the H2 sense. Okay, so that's the theorem. Now, before coming to the proof, let's just try to understand a little bit further what's the spirit of this result. So in a way, this is something that one calls a smoothing property, or is a higher regularity result for the Laplacian, because in the understanding of lecture 2 and 3, the domain here, these are all H1 functions with an additional property, and then the setup of this operator, in the special case that you're working on Rn, forces you to be in H2. It's an if and only if. So the functions are more regular than what you would expect just from the definition. On the other hand, the regularity is precisely what you expect if you would not know about form methods. Then you would say, of course, if I want to define a Laplace operator, I need H2 as a domain. Okay, so using a Fourier transform, we're going to see that indeed these two things are the same. Okay, the smoothing property has to do something with the regularity of the coefficients. Okay, so in this special case, the coefficients are just identity matrix and they're constant. Okay, so this works because there's nice coefficients in this operator. If the coefficients are just L infinity, then this property can fail badly. When you just have L infinity coefficients. In fact, in the exercises, we're going to make an example where this fails in the worst possible way. Namely, we're going to make the intersection of the domain of the operator with these coefficients and H2 trivial. So the only H2 function in the domain of the operator is going to be the zero function. It's the worst possible scenario, and this is possible because the coefficients are very irregular, but still L infinity and elliptic. Okay, and another thing that you're going to see is this smoothing property really becomes challenging only in superior dimension. When you're working in one dimension, then the smoothing property works for the directly Laplacian on any open set. But this is very specific to the one-dimensional setting, and you are invited to figure out exactly why and how. This is one of the exercises. And this is also one of the exercises. Okay, I went all in for this exercise and figuring out some crazy construction of Walter Rudin, so please do the exercise. Okay, and so let's see how the proof goes. Proof of 4.6. Point should be sitting here. Okay, so let's prove this inclusion first. So let's assume that I am giving an element in the operator in our language, and let's see what we can do with it. Okay, so let's suppose uv is contained in the operator view as a linear relation as always, and let w be a Schwarz function. Okay, now I have to do some integration by parts magic, and I have to figure out that u actually is in H2, and for this, of course, I'm going to use the newly obtained characterization of H2. Okay, so I'm starting maybe with the integral on Rn, and I do v times w. Okay, do I want to do it like this? No, I don't want to do it like this. I want to do it with Fourier transform first, and I want to do the xi, but of course by Plancherel this is the same as doing it without Fourier transform. Okay. So this is Plancherel. And why do I start with the Fourier transform? Because I want to check that u is in H2, but I want to do the Fourier characterization of H2. And so therefore I should be, in the end, say something about Fourier transforms. Okay. So now I can use the definition of the operator, right? Because this is a L2 inner product, so it's the H inner product of V against this W guy, which in particular is in H1. So the definition of the operator says that this is representing the associated sesquilinear form, and the associated sesquilinear form would be this, but with a U. Okay. U is in the domain of the operator because the sesquilinear form is represented by the L2 inner product using the function V. Okay, well, now I can do Plancherel backwards and turn this again into an integral over Rn on the Fourier side. So I have to put Fourier transforms here and here. Then Fourier transform of the gradient gives me 2 pi I xi as a vector, and I get it twice from these two terms. So I'm getting 4 pi squared absolute value of xi squared times u hat v w hat bar d xi. Right. This is 2 pi I xi times 2 pi I xi conjugate gives you precisely this guy. Okay, now this is, a situation that you were very well aware of. What you want to prove is that this guy is equal to this guy. So you have to make sure that these guys can be any test function in order to apply fundamental lemma in the calculus of variations. And of course, once again, this can be any phi in CC infinity if you just take again W to be phi inverse conjugate. Okay, it's the same trick. It's just enough functions for which we checked something to say that these two functions, the blue ones, are the same. Okay, so this means that v hat is 4 pi squared xi squared u hat. Fantastic, but u, by definition, is in L2. It was even H1. I want to check that it's in H2, so I refer to this calculation, or this proposition. I have to check that xi squared times u hat is an L2 function. But guess what? Xi squared times u hat is just sitting here. It's equal to this function, and this is the Fourier transform of an L2 function, because v was the image of u under the operator, and it was an operator in L2. Okay, so because this guy here is L2, we can use the 4.5 proposition to conclude that u is in H2 on Rn, and we can do even more. Namely, we we know that V is minus Laplacian of U in the H2 sense. Because if I take, this is now defined in H2, I take Fourier transform, gives me V hat, and the Fourier transform of this, or the symbol of the negative Laplacian, is precisely this. Okay? So it means that whenever I'm in the operator in the variational sense, the U is in H2, and the action of the operator is just the H2 sense Laplacian. So this gives me one inclusion. Now I have to go backwards, but going backwards should be very easy if I remember correctly. So if I want to go backwards, I just have to check that if U is in H2 on Rn, I have to see that U and V defined as the H2 negative Laplacian, that this thing is in the domain of the operator. Okay, but you see if U is in H2, and this calculation I wrote over there, this guy here is then going to be minus del, this is going to be V hat, right? So this line, the first two things, they are the same by the choice of this U and V. And the calculations in between, they are still valid, because from here to here, I can just do the calculations backwards. Okay, and so I end up that precisely all these things on the board, they are valid for this choice of U, provided I take V as the H2 Laplacian. And so this means that calculation above gives you UV in minus delta H1 Rn. Simply because the identity of these four terms can be checked completely on the Fourier side. But then if you read what you're going to get from the second to the third term, you have verified precisely that this thing is contained in the variational operator. Okay. Finally, so we checked the domain, we checked the action of the operator, we also get the equivalence of the graph norms, because the operator, I mean, this is just a symbol of the Laplacian, and then when you see what we're doing here, the H2 norm is equivalent to taking U in L2 and Laplacian in L2. Okay, so equivalence of the graph norms is for free. Questions? You have a question? You was like, I thought the cameraman wanted to know something. Okay, so we'll make it proof complete. Okay, what does this proof say? I claim that the proof says something else that's going to be very useful for what I'm doing in the final minutes of today and what we're going to do a lot on Wednesday. Let me just check the timer. Oh, perfect. You stop me if I'm too quick. I get the impression I'm running because nobody stops me. So you see from this calculation, there's a specific function on Rn, namely m of psi being 4 pi squared psi squared. This function plays a very particular role in all of these considerations. Because what we've seen is I take any element in the domain of this variational Laplacian, I take its Fourier transform, I multiply by this function m, I take the inverse Fourier transform, then I'm getting precisely back the image of U under the operator. And the calculation also works in the other way around. If I have any L2 function, I take Fourier transform, And it happens to be the case that after multiplying by this function, I stick in L2, then the other inclusion has shown us that this means that u is in the domain of this variationally defined Laplace operator. And Laplacian minus Laplacian of u is precisely inverse Fourier transform of this. So if you want to write this as a commutative diagram, you see that there is L2 of Rn. In L2, you can apply the partially defined operator minus delta. Is an operator in L2. But if you switch perspectives and apply Fourier transform, then in frequency space, the action of this operator is just the multiplication operator associated with this m. Okay, and you see here I'm writing now, from now on, I write minus delta instead of minus delta variational guy. Okay, so when minus delta, and I write minus delta and I want to talk about it as an operator in L2, I mean the variational operator, either defined as in lecture 3 or defined as what comes up from this theorem. The most beautiful perspectives of all is to see that in virtue of this commutative diagram, minus delta is just Fourier inverse multiplication operator Fourier transform in the sense of unbounded operators. In other words, the domain of minus delta are all elements in L2 such that the Fourier transform lands in the domain of the multiplication operator, and then you take Fourier transform backwards. Okay? In other words, minus delta is unitarily equivalent to the multiplication operator by the multiplying function m. And this is just a reinterpretation of what I've shown to you. Now, this is very interesting because now you have the same operator and you have two completely different perspectives which allow you to do completely different things. Right? If you stay on this side, then it's all about differentiating functions because it's a differential operator. You can do things like differentiating functions don't have an analogon on this side. But on this side, you just multiply by a function and you can do much more complicated operations, possibly, by looking on multiplication operators than differential operators. Okay. You also know a lot of things for free concerning spectra, resolvent, that we also proved in the meantime using the variational thing, but the equivalence to this operator allows you to transfer anything that you can do with a multiplication operator to something you can try to do with a Laplace operator. Okay, and this is what we're going to explore when we talk about functional calculus for the first time. Hopla. So, 4.3 is called a first glimpse on functional calculus. Okay. Remember that at some point I told you, at some point was the beginning of the lecture, I want to define something like a square root or fourth root of minus delta. It was mysterious what should be a fourth root of a differential operator. It's much less mysterious to say what should be a fourth root of a multiplication operator. Okay, so this is going to be the game that we're playing. But before we get there, we just do one more thing as a very basic example of exploiting this equivalence of minus delta to a multiplication operator, which goes as follows. Okay, so you know that you can define integer powers of an operator Okay, so there's a domain of minus delta to the k, and the question is, what is this space? I'm asking the Darmstadt team, because you can't see that, but there are at least 100 participants in the lecture hall. What should come out here? Make a guess. What happens if you take powers of m? If you apply if you square the operator, it's going to be equivalent to the multiplication operator squared. But multiplication operator squared is just the multiplication with the squared symbol. So if I square this multiplication function m here, I get a constant and I get a psi absolute value to the 4. Now, being in L2 and being such that the Fourier transform can resist psi to the power of 4 without going out of L2, according to proposition 4.5 over there, means that the function is in H4. Okay, so more generally, we're going to have that this is H2k of Rn whenever k is positive integer. Okay, and so the proof is extremely simple. You see from this equivalence to multiplication operator that minus delta to the k is equivalent, according to 4.8, to the multiplication operator to the k. Fourier transform, but multiplication operator associated with m to the k is just the same thing as the multiplication operator with multiplying functions m to the k. Okay, and m to the k is up to a constant. Up to constant is psi to the 2k, so this is 4 pi squared to the k times psi to the 2k. Okay, I mean the domain of this operator consists of all L2 functions. I can multiply with this guy as they in L2, so up to doing Fourier transform on both sides is precisely the same thing as being in h to the 2k, because this is precisely defined by the same symbol. Okay, so I can use 4.5 yields the claim. Okay. And so this is a very basic example where a manipulation, I sort of think of this as plugging the operator minus delta into the power function that raises a number to the power k. We played this back to a property of the multiplication operator because on the multiplication side we know exactly the domain of this. Now the interesting thing is that on the multiplication side it doesn't even matter that I raise something to an integer power here. Raising m to any power alpha could be a meaningful operation, whereas raising the Laplace operator to any power is something we don't understand at this point. Okay, but because the two objects are equivalent, something like raising the multiplication operator to any sort of power would give us a very natural definition of what raising Laplace operator to the respective power should be. Okay, and this is precisely what we're going to do when talking about functional calculus for the first time in the lectures. Okay, so you will see, and we're going to have, I think, 5, 6, 7, 8 lectures on functional calculus, where we're going to do it very systematically for holomorphic functions and sectorial operators. But at this very point, when you see the first time, just think of it as a way of define functions of an operator L, like for example a square root of L, or fourth power of L, or square root or fourth power times an exponential of minus a square root. Okay? It's like plugging the operator into functions. And while we're going to do it for sectorial operators and specific classes of functions in the next lectures, here we're going to stick with the negative Laplacian on the full space, and we're going to use the Fourier analytic characterization of this operator over here to set up a functional calculus. Right? Because if I want to plug L into a function f, so I want to define something like f of minus delta, I just play it back to over here, and I do composition of m with the function f. Okay, so this is the definition that we're doing. Let f be a measurable function on the closed interval from 0 to infinity, because this is where this m takes its values. And then I'm going to define f of minus delta. I want to define it as an operator in L2. And now, just as in this example, where raising the power k went down to composing the function m with a power function that raises everything to the k, I'm inspired by this, and I define it as the operator that, in virtue of the Fourier transform, is equivalent to the multiplication operator with the function f composed with m. Okay, in other words, f of minus delta is Fourier inverse m f circ m Fourier. And this is the multiplication operator with maximal domain in L2, and this operator then has as domain all functions that after Fourier transform end up in the domain of the multiplication operator. Okay, this defines a closed operator in L2. You agree? Now I run out of the things that I knew by heart I wanted to tell you. Now I have to see what I should tell you next. Okay, there's not much more to say for this lecture than to... it's a very bad ending of a lecture to do like that. Anyway, okay, so this is definition, and what this definition creates is a map sending functions to linear operators, in the sense that you morally plug in the operator into the function. And so this is a map that goes from measurable functions on 0 infinity to closed operators in L2. Okay. Now, this map, you can always define things, but then it's a question of whether definition is useful for anything. In other words, if I want to really benefit from this map, then the highest goal that has absolutely to be achieved is that the transference between functions and operators works in such a way that I can do calculations with these operators as if I would do calculations with functions. For example, I should be having relations that say, if I do multiplication of two functions, that should be translated into composition of the respective operators. So there should be a structure like some sort of algebra homomorphism. Okay, we're going to stay a little nebulous at this point. There's going to be an exercise on it where you show that if you restrict to bounded functions, then L infinity is an algebra, and the thing becomes an algebra homomorphism from L infinity into bounded operators on L2, because you know that bounded functions correspond to bounded multiplication operators, and even though M is not bounded, if I do composition with a bounded F, becomes bounded. When it goes to closed operators, in particular unbounded operators, then you have to be very careful what you actually mean by algebra homomorphism, and you have to reduce, or you have to lower significantly your expectations of what could possibly be true, because already in the first lecture in the exercises you had this thing that shows that sums of closed operators already poses a problem. Okay? And so this issue we put aside for one more week, and Robert is going to tell you systematically in lecture 5 what the notion of an algebra homomorphism should be when you're dealing with closed unbounded operators. Okay, so we stop here for today, unless you have further questions. And so what I want to do on Wednesday with you is I want to use this functional calculus, and I want to look at some very specific functions, in particular fractional powers. Fractional powers like minus delta to the alpha, for alpha a real positive number. These are well-defined functions. In this class here you can apply the functional calculus. It gives you fractional powers of the operator. And then we're not stopping here, but we're going to determine the domains of these fractional powers to see that the calculus really gives you very meaningful and concrete objects if you're trying hard for the Laplacian. And then in the second part of next lecture, we're going to use functional calculus to prove some interesting reproducing formulas. I'm going to tell you what that is. And they're going to be very important when we talk about general functional calculus later on. Okay, so stay tuned until Wednesday, and then functional calculus from lecture 5 on. Okay, that's it for today.